beneath the Western Pacific lies a chasm that defies human scale. More than 10 kilometers deep, the Mariana Trench opens like a dark gash in the Earth's crust, a place where the pressure is so brutal that the human body would be destroyed in an instant, and where, for a long time, science believed that life simply could not exist. For decades, what was known about that world buried underwater consisted of mere fragments of data, cold numbers jotted down in logbooks, and echoes returned by instruments that never actually saw the bottom. Before discussing submersibles and high-pressure cameras, it's essential to understand that initially the trench was just an odd number in a column of measurements. To grasp how we even began to suspect the existence of this abyss, we must go back to a time when the deep ocean was practically a blank space. In the 1870s, the British Royal Navy ship HMS Challenger set sail on what is now considered the first major global survey of the oceans. It wasn't a heroic expedition in the romantic sense, but rather a methodical and repetitive undertaking, measuring depths, taking water and sediment samples, recording temperatures, and analyzing currents. Day after day, the scientists and sailors on board repeated the same routine, transforming an unknown sea into a series of columns of data. Each depth measurement was a test of patience and physical strength. A lead block attached to an extremely long graduated rope was lowered over the side and disappeared into the darkness. Then came the hard part, hauling all that weight up by hand, mark by mark, while the ship bobbed under the tropical sun or through biting winds in cold latitudes. It was a slow procedure prone to error, but it was the best that the technology of the time could offer. Each reading represented hours of effort and the constant risk of losing the line, the weight, or even men overboard. Most of those readings told the same story: a wide and relatively uniform ocean floor, carpeted with mud and sediment, some 3 or 4 kilometers below the surface. The deep ocean began to take shape as an immense, monotonous and silent plain, dotted here and there with volcanic uplifts and mid-ocean ridges, but in general more boring than the legends suggested. However, in a remote region of the Western Pacific, thousands of kilometers from Japan and far from any coast, a routine measurement ceased to be so. The rope descended 1 kilometer, then 2, then 3. It continued to descend 4, 5, 6 kilometers, and the weight continued sinking without touching the bottom. On deck, the sailors kept letting out line while the hull creaked softly over a void of which no one had a clear image, only the intuition of something immense and unknown beneath their feet. There were no detailed maps. Modern sonar didn't yet exist. Only a ship of wood and metal suspended over a blackness from which only the whisper of the wind on the surface reached. In those days, sailing far out to sea already involved considerable risks. Storms capable of wrecking a ship, invisible reefs, irreparable damage far from any port. Added to this was the fear of the unseen. Tales of sea monsters with giant tentacles and impossible creatures were not just naive superstition. They were a way of giving shape to ignorance, of filling the void of information with images. The depths were imagined as a hostile space, populated by deformed beings and inexplicable forces. In that context, dropping a rope into an abyss that seemed to have no end must have been as unsettling as it was fascinating. Each additional stroke of rope was a reminder of how little was known about the world hidden beneath the keel. After a long wait, the lead weight finally reached the bottom. When they calculated the depth from the length of the line, they obtained an extraordinary value: 4,475 fathoms, a little over 8 kilometers below the surface. never before had such a figure been recorded in the oceans. That point was marked on maps with a name that would become legendary: Challenger Deep, in honor of the ship that had revealed the most breathtaking chasm on the planet. Suddenly, the seabed was no longer just a uniform plane. It had a point that seemed almost bottomless compared to the rest. At that moment, no one knew that this measurement didn't even reach the true center of the abyss. The method, based on ropes and weights, was imprecise and vulnerable to currents that could tilt the line and alter the calculation. For decades, that figure remained a record, but also a source of suspicion. Was that really the limit, or did the ocean hide something even deeper? Many decades later, when technology allowed the use of sonar and other remote sensing instruments, scientists returned to the region. This time they relied not on the strength of arms or the patience of sailors, but on sound pulses sent to the seabed that returned laden with information about the underwater topography. The new data showed that the Challenger's initial measurement had only scratched the surface of an even deeper depression. The true lowest point of the Mariana Trench lies nearly 11 kilometers below sea level. To put this into perspective, a simple comparison is often used. If Mount Everest, at approximately 8.8 kilometers high, were placed at the bottom of the trench, its summit would still be submerged under nearly 2 kilometers of water. Down there, the pressure exceeds 1,000 times the atmospheric pressure at sea level. Every square centimeter of any surface is subjected to a weight equivalent to tons. The trench is not an isolated pit, but an elongated curved structure that follows the western edge of the Pacific Ocean. Something like a scar marking the contact between two large fragments of the Earth's crust. At its widest points, it reaches almost 70 kilometers in width. One side drops off like a nearly vertical wall, the other slopes more gently, merging into the abyssal plains. Challenger Deep, despite being only a small section within this gigantic crevice, could house dozens of skyscrapers stacked on top of each other without ever reaching the surface of the ocean. Viewed from space, Earth appears as a relatively homogeneous water planet, a smooth blue sphere. But beneath that surface lies a topography as extreme as any continental mountain range. Underwater mountains, canyons, plains, and, in the case of the Marianas, a chasm that pierces almost the entire oceanic crust. The origin of this fissure is not a random fracture, but rather the slow and constant movement of Earth's crust. The outer part of the planet is not a continuous solid layer, but a mosaic of enormous tectonic plates that move a few centimeters per year over the hotter, more plastic mantle of the interior. Where the plates separate, magma rises, cools, and forms new ocean floor. There, the seafloor is made. Conversely, where the plates meet and collide, the crust cannot continue to accumulate indefinitely, and one of the pieces must give way, sinking beneath the other. It is this process, the slow and silent subduction of one oceanic plate under another, that has excavated over millions of years the deepest abyss on the planet. At many ocean margins, the older, cooler plate sinks beneath a lighter one. This plate bends, cracks, and begins a slow descent into the Earth's interior. This is the process of subduction, responsible for the deepest ocean trenches on the planet. Every time one plate bends and sinks beneath another, the surface leaves a clear sign, a long, narrow trench marking the point where the crust begins its descent back into the mantle. In the case of the Mariana Trench, the main player is the Pacific Plate, one of the largest and densest on Earth. For tens of millions of years, it has been moving westward, slowly pushing its own crust toward the edge where it meets the smaller, lighter Philippine Plate. The Mariana Islands volcanic arc lies along this boundary. There, the Pacific plate fails to push the islands outward. Instead, it bends and slides beneath the neighbouring plate. At that inflection point, where solid rock bends on a planetary scale, the trench is born, a colossal fold carved into the base of the ocean. This subduction pattern is not unique to the Marianas. Bordering the Pacific, other plate boundaries exhibit the same dynamics, and together form a large ring of trenches, island arcs, and volcanic chains known as the Ring of Fire. Nearly 90% of the planet's earthquakes and approximately 3/4 of its active volcanoes are concentrated there. Within that ring, the Mariana Trench represents one of the most extreme and striking examples of the power with which tectonics can reshape the Earth's surface. Understanding how the Mariana Trench formed is only half the problem. The other half begins when someone attempts to physically reach its bottom. At nearly 11 kilometers deep, the true enemy is not the darkness or the distance, but an invisible force that permeates everything: pressure. Even in something as commonplace as the bottom of a swimming pool, it is already perceptible. Just a few meters below the surface, your ears pop and your chest feels a slight additional weight. At 10 meters, the pressure has doubled compared to that at sea level. If this same logic is extended to the scale of Challenger Deep, the figures cease to be intuitive and become extreme. At the deepest point of the trench, the column of water above generates a pressure more than 1,000 times greater than atmospheric pressure, on the order of roughly 16,000 pounds per square inch. Under these conditions, any object not designed with an enormous safety margin risks sudden collapse. The smallest structural flaw, an imperfect weld or a screw that was not properly calculated, can become the source of a catastrophic failure. Even equipment specifically designed for the deep ocean has proven vulnerable. In 2014, an unmanned research vehicle exploring the Kermadec Trench at almost 9,900 meters abruptly lost contact. The signal was cut off, no further data were received, and the only things recovered afterward were scattered fragments of the machine. Pressure had found its weak point. The comparison with modern military submarines is illustrative. These vessels, built to operate in war zones, typically work safely at depths of only a few hundred meters. Even the deepest diving models have strict limits well before reaching a kilometer. Beyond those depths, the risk of structural failure increases exponentially. Challenger Deep, on the other hand, plunges almost 11,000 meters below the surface, an environment completely beyond the reach of any existing naval submarine. Reinforcing the hull is not enough. It is necessary to conceive of a completely different type of vehicle, designed from the outset to withstand pressure that ruthlessly crushes anything unprepared. In this context, a solution emerged that was as simple in concept as it was extreme in its execution: the Bathyscaphe. In the late 1950s, the Swiss engineer Auguste Piccard developed the Trieste, a vehicle that combined two key elements. At the bottom, a thick-walled steel sphere, barely large enough for two people to sit, huddled together. This small bubble would be the only habitable space, pressurized to the surface level above an enormous float filled with gasoline. The choice was not accidental. Gasoline, less dense than water and highly incompressible, provided buoyancy even under extreme pressures. Between the sphere and the float was attached a support structure to which iron tanks were fixed as ballast. The operating principle was straightforward. The Bathyscaphe was ballasted to sink, and once at the bottom, it released some of that weight to ascend. There was no sophisticated propulsion system or great comforts. It was essentially a sturdy sphere suspended from a floating tank. The rest was patience, calculation, and a good dose of confidence that the equations guiding the design were correct. In 1960, 2 men sat inside that sphere to undertake a dive that would mark a turning point in history. John Walsh, a lieutenant in the US Navy, and Jacques Picard, a Swiss oceanographer and son of the vehicle's designer, began their descent to the deepest point on Earth. Once the hatch was sealed, the sphere was isolated from the world. There was no room to stand. They could only look out of small glass windows whose integrity depended on preventing even the smallest microcracks from becoming a lethal problem. As the Trieste began to sink, the sea above faded into a distant memory. The journey to the bottom was not quick. As they descended, the temperature dropped and the pressure increased in a continuous gradient. Inside the sphere, Walsh and Picard watched the numbers on the depth gauge advance. 1,000 meters, 5,000, 8,000. Each number represented a layer of water accumulating above the steel hull. There was no way to open a hatch, to immediately retreat, to abort the descent in the conventional sense. The only option was to trust that the structure would hold until it hit the bottom. At nearly 9 kilometers, a sudden explosion shook the submersible. The sharp, violent sound echoed like a gunshot inside the cramped cabin. For a few moments, any theoretical calculations must have been overshadowed by the primal sensation of being crushed. It was later discovered that an outer plexiglass panel, installed as additional protection, had cracked under the pressure. The main cabin, however, remained intact. The dive continued. After almost 5 hours of descent, the Trieste finally touched down at the bottom of the Challenger Deep. The impact threw up a cloud of extremely fine sediment that clouded the water in front of the small windows. For a few moments, only a kind of milky mist could be seen, a liquid dust suspended in the darkness. When that cloud began to dissipate, the scene that emerged was not that of a completely lifeless mineral desert. According to Picard's account, a flatfish-like creature about 30 centimeters long was moving across the seabed. Viewed through a pane of glass only a few centimeters wide and under immense pressure, this observation was necessarily limited, but sufficient to draw a decisive conclusion. Even at the deepest known point, life was present. Walsh and Picard remained at the bottom for about 20 minutes. They couldn't travel great distances or perform complex maneuvers. The main mission wasn't to map the trench, but to demonstrate that it was possible to reach it alive and return. After that brief interval at the ocean's most extreme point, they released their ballast and began their ascent. The return to the surface took about 3 more hours, traversing, in reverse, the layers of water that separated them from air and light. When they finally emerged, they had not only set a historic record, they had forced science to reconsider the idea that life could not withstand such high pressures. Paradoxically, the success of the Trieste was also a kind of endpoint. The dive proved that the journey was possible, but it also made it clear that the level of risk and the technical difficulties were enormous. For more than half a century, while humanity conquered the summit of Everest and reached the moon, the bottom of the Mariana Trench remained virtually untouched. No human being set foot on Challenger Deep again for decades. It wasn't until 2012 that the second manned dive to the absolute bottom of the ocean took place. More than half a century after the Trieste, the protagonist was no longer a military project or a purely technological experiment, but a film director obsessed with the depths, James Cameron. Aboard the modern submersible Deepsea Challenger, he undertook a solo descent to Challenger Deep. His vehicle was radically different from the Trieste's metal cylinder. It incorporated lightweight and resistant composite materials, advanced electronic systems, high-density batteries, high-definition cameras, and an arm capable of collecting samples from the seabed. It wasn't just about getting there, but about observing, recording, and bringing something of that world back to the surface. Cameron became the third person to reach the deepest point of the Mariana Trench, but his journey had a deliberately scientific focus. During the hours he spent at the bottom, he filmed with 2D and 3D cameras, recorded the physical characteristics of the terrain, searched for signs of life, and stored sediments and rocks in compartments designed to withstand extreme pressures. Every design decision on the Deepsea Challenger was dictated by the constraints of its environment. An elongated, almost torpedo-like shape to reduce drag during descent and ascent, a tiny pressure sphere barely large enough for the pilot to minimize the volume exposed to the pressure, and redundant ballast and buoyancy systems to ensure a safe return. The result was a dive that combined exploration, technology testing, and scientific data collection. His descent had another effect that can't be measured in meters or pressure bars. It rekindled public and academic interest in the abyssal trenches, what for decades had been an isolated record. From 1960 came to be seen as the beginning of an era, not as a one-off event. From then on, a new generation of submersibles and expeditions began to visit the abyss more frequently. By the beginning of the 2020s, more than 20 people had descended to Challenger Deep, easily surpassing the total accumulated in the previous 50 years. Among these expedition members were explorers like Victor Vescovo and Hamish Harding, who set records for the number of descents and the length of operational time at the bottom, carrying out series of dives that allowed for the comparison of data between different dates and sectors of the trench. These new expeditions incorporated high-resolution bathymetric maps, chemical and biological sensors, and more precise navigation systems than those available during the Trieste expedition. Instead of a single isolated dive, entire campaigns began to be planned. Multiple descents, slightly different routes, systematic sample collection, and the deployment of autonomous instruments that remained at the bottom for hours or days. Even so, each descent remains a complex, expensive, and vulnerable operation. No technology has managed to turn Challenger Deep into a routine destination. Each dive remains, in practice, a massive undertaking. It requires years of design and construction of the submersible, exhaustive testing of every component in pressure chambers and test tanks, independent certifications, and failure simulations. On the surface, support vessels equipped with cranes capable of handling tens of tons are needed, along with laboratories to process samples, redundant communication systems with the submersible, and specialized personnel in navigation, electronics, mechanics, logistics, and medicine. A valve failure, a small crack in the pressure hull, a short circuit in a critical system, or a miscalculation in the ballast can mean the loss of the vehicle, the data, and, in the worst-case scenario, human lives. Although submersibles capable of repeatedly visiting the abyss already exist, the total number of hours humanity has actually spent at the bottom of the trench is minuscule compared to the vastness of the place. Each descent offers only a narrow glimpse, like the beam of a lantern in a completely dark cathedral. Meanwhile, on the surface, none of that complexity is visible. Above the Mariana Trench, the Pacific Ocean appears as an endless sheet of water, with no coastline in sight and no landmarks visible. All is a uniform horizon, repeating waves, sky and sea blending in the distance. But once you leave that surface, the ocean ceases to be a homogeneous volume and reveals itself as a stratified space, divided into well-defined layers, each with its own light, temperature, pressure, and life forms. What from above appears as a single body of water is, in reality, a superposition of distinct worlds. The first of these layers is the epipelagic zone, the ocean's luminous skin. It extends from the surface to a depth of about 200 meters. It is a relatively thin band compared to the thousands of meters below, but it plays the most crucial role for life on the planet. It is the only layer of the ocean where sunlight is intense enough to sustain photosynthesis continuously. Here, solar radiation penetrates strongly, the water mixes due to the wind and waves, and the temperature undergoes daily and seasonal variations that influence the entire marine system. In this epipelagic zone, billions of tiny organisms like phytoplankton, cyanobacteria, and microscopic algae convert sunlight, dissolved carbon dioxide, and nutrients into organic matter and oxygen. They are the foundation of the marine food chain. Zooplankton, small fish, large predators, and ultimately, many of the fisheries on which humans depend all rely on them. On a planetary scale, their impact is even greater. Almost half of the oxygen in Earth's atmosphere is generated in this layer, which rarely exceeds 200 meters in thickness. Every time a pulse of light reaches the surface above the Mariana Trench and passes through this upper layer of water, it activates, however minimally, the same biological machinery that sustains the climate, regulates carbon, and makes it possible for the rest of the ocean, even its deepest reaches, to be part of a living system. Phytoplankton becomes food for zooplankton, tiny creatures that drift with the currents, copepods, crustacean larvae, and minuscule jellyfish. In turn, this zooplankton is eaten by small fish and larger jellyfish. They, in turn, feed larger predators such as pelagic fish, squid, and sharks. In this way, the marine food chain rises from its microscopic base just below the sunlight. Life in the deep sea depends, to a large extent, on the productivity of this surface layer. Remains of organisms, excrement, tissue fragments, and aggregates of organic matter sink slowly like a dark rain, a marine snow that nourishes the lower levels of the ocean. As you descend from the surface, the colors begin to fade. First, the reds disappear, then the oranges and yellows, until only a deep blue filtered by the water remains. At around 200 meters, even that blue becomes faint. Here the epipelagic zone ends, and the mesopelagic zone, also called the twilight zone, begins. Light from above still exists, but it is so weak that it no longer allows for photosynthesis. The temperature drops rapidly and the pressure begins to increase more noticeably. In this constant semi-darkness, the first flashes appear, green and blue bursts of bioluminescence that emanate from the organisms themselves and pierce the gloom with brief pulses of light. Despite its apparent darkness, the mesopelagic zone is extraordinarily rich in life. Some estimates suggest that the biomass of fish inhabiting this zone exceeds that of the rest of the ocean combined. Here you'll find gigantic schools of lanternfish, animals that spend the day hundreds of meters deep and at night ascend in massive vertical migrations to feed in shallower waters. This daily migration, hundreds of meters up and down, is one of the largest collective movements of animals on Earth, though it is almost never visible to the human eye. When you descend to approximately 1,000 meters, sunlight disappears completely. There is no difference between day and night. You enter the Bathyscaphe zone, also known as the midnight zone or the twilight zone. The temperature stabilizes a few degrees above freezing, while the pressure reaches values hundreds of times greater than at the surface. Conventional submarines can no longer operate here, as their hulls are not designed to withstand such pressure. And yet, this place is not an uninhabited void. In the absolute darkness, flashes of bioluminescence multiply. Jellyfish, squid, fish, crustaceans and worms transform the ocean into an inverted sky filled with moving points of light. The zone of water between 1,000 and 4,000 meters deep constitutes the largest continuous habitable environment on the planet. Its inhabitants have shaped their bodies and behaviors to survive conditions that humans could not endure. Their skeletons are lightweight, sometimes reduced to minimal structures. Their tissues are flexible and adapted to the pressure. Their metabolisms have slowed to conserve energy in an environment where food is scarce and arrives irregularly. The senses have also been reinvented. Giant eyes optimized to capture the faintest trace of light, pressure, sensitive organs, antennae and tentacles that scan the water for chemical or mechanical signals. In this dark realm, light becomes an essential tool. Some fish have developed astonishing eyes. The barrel-eye fish, for example, has a transparent skull that functions like a dome. Through it, its tubular eyes can rotate and look upward for silhouettes against the faint glow that drifts down from the upper layers. Other predators use light not only to see, but to attract. The deep-sea anglerfish carries a bioluminescent filament on its head, a tiny lantern that floats like a glowing worm. When prey approaches, drawn by this single point of light in the total darkness, it suddenly finds itself facing jaws full of long, sharp teeth. The deep-sea dragonfish, meanwhile, emits light along its body, creating a luminous silhouette that serves to disorient and lure its prey before it attacks. Deeper still, in even quieter parts of this zone, hangs the long-armed squid. Its central body is small, but its tentacles unfurl like threads that descend vertically many meters into the darkness. It remains almost motionless, its arms outstretched like a network of sensors awaiting the slightest touch of prey. Occasionally, deep-sea cameras have managed to capture its ghostly silhouette, floating motionless in the water like an inverted kite tethered to nothing. Even stranger is the siphonophore, one of the most perplexing creatures of the deep ocean. At first glance, it resembles an elongated jellyfish, with some species exceeding 40 meters in length, longer than a blue whale. But it is not a single organism, but a colony, a chain of genetically identical units, each specialized in a specific function, such as propulsion, prey capture, or digestion. Together they form a collective body that drifts slowly in the darkness, often emitting light along its entire structure. When a giant siphonophore coils up on itself in the depths, it draws undulating luminous patterns that seem alien to any terrestrial reference. At a depth of about 6,000 meters, an almost invisible threshold is crossed. The bathypelagic zone ends and the Hadal zone begins, the exclusive territory of the great ocean trenches. Here the water hovers just 1 degree above freezing, and the pressure approaches 1,000 times atmospheric pressure. Every square centimeter of any surface experiences a force that, on a human scale, would be inconceivable. Even so, the Hadal zone is not completely isolated. Along the bottom of the trench circulate currents of cold, very dense water that have sunk in polar regions and slowly crossed half the planet before reaching this point. These deep water masses carry dissolved oxygen with them, maintaining a minimum level of habitability even in the most extreme corners of the ocean. This slow and silent circulation is the thread that connects the abyss to the rest of the Earth system. In a place where light never reaches, life can no longer depend solely on food falling from the surface. Marine snow remains important, but it's not enough. At certain points on the ocean floor, seeps of fluids rich in chemical compounds such as hydrogen sulfide, methane, and other reduced elements, escape from the oceanic crust and upper mantle. There, communities of microorganisms use these compounds as an energy source, transforming inorganic matter into biomass through chemosynthesis. It's a process analogous to photosynthesis, but fueled by chemical energy instead of sunlight. Much less efficient, yes, but sufficient to sustain small food webs in an environment where every resource counts. On this microscopic foundation, discrete communities are built, almost invisible on a human scale. Among the most characteristic inhabitants of the Mariana Hadal Zone are snailfish, small animals with soft bodies, a milky white color, and minimal bone structure. Their gelatinous tissues and sparse bones are extreme adaptations to crushing pressure. By reducing rigid parts, the risk of fractures and internal collapses is decreased. Snailfish have been recorded in the Mariana Trench at depths close to 8,000 meters, moving with gentle movements along the bottom and between the walls of the submarine valley. However, below approximately 8,200 meters, a live bony fish has never been observed. This depth marks, as far as is known, the final biological boundary for this group in the deep ocean. It is believed that beyond this limit, the pressure alters the proteins and cell membranes of vertebrates to such an extent that their physiology ceases to function. What for humans is just a number, for marine life translates into an invisible wall, a depth range that some lineages have managed to conquer and others have not. At the very bottom of the Challenger Deep, where the trench reaches its greatest depths, life seems to shed all excess. Large fish disappear, complex bodies become rare, and the ecosystem simplifies in appearance, almost reduced to microorganisms and a few specialized invertebrates. Among the latter, amphipods stand out, small crustaceans that appear fragile but are extraordinarily resilient. Observation cameras baited with pieces of fish have recorded swarms of these animals descending upon the food in a matter of minutes, demonstrating that even in the most remote abyss, the opportunity to feed is never missed. However, the amphipods visible alongside the bait tell only part of the story. The most common method for observing life in the trenches involves dropping cameras to the bottom with a lure, waiting a few hours, and retrieving the equipment. This means that most of the images obtained show a small circle of artificially illuminated terrain and a community filtered by the type of food offered. Scavenging crustaceans are known to quickly flock to this free resource, but that doesn't mean they are the only inhabitants of the place. They are simply the ones that react to the available stimulus during the brief interval that the lights are on. More inconspicuous, clinging to the substrate itself, are perhaps the strangest organisms in the entire abyss, xenophyophorids. At first glance they appear as shapeless blobs, gelatinous masses coated in mud and attached to rocks or sediment. But each of these structures corresponds to a single giant cell, capable of reaching the size of a human fist. To build their fragile shells, these organisms agglomerate tiny particles of sediment, mineral fragments, and remnants of other living things. They then filter the smallest organic particles from the water, which constitute their food. The interest aroused by xenophyophores goes far beyond simple biological curiosity. Their ability to maintain functional, flexible, and repairable cell membranes under pressures that would deform most known structures offers important clues for materials, science, biotechnology, and medicine. Understanding how they protect and repair their DNA under these conditions can inspire new strategies against cell surface damage, from techniques for preserving tissues to innovative approaches for treating diseases related to genetic stability. In a way, each giant cell at the bottom of the trench acts as a natural laboratory, where life tests solutions that have not yet been imagined on land. Despite the technological advances of recent decades, our knowledge of this world remains fragmented. Most of the available data on the deepest trenches comes from a very limited number of dives and automated cameras that record only tiny areas for short periods. At the bottom of the Challenger Deep, it is assumed that only microorganisms and invertebrates can withstand the extreme conditions. But even that assertion is based on limited evidence. Humanity has almost never spent enough time there to state anything with absolute certainty. This scarcity of observations makes the trench a scientific territory fraught with uncertainty. What other as yet undescribed species inhabit its walls and depressions? What biochemical mechanisms allow a cell to continue functioning under pressures of up to 16,000 pounds per square inch, near freezing temperatures and total darkness? What kinds of ecosystems form around as yet undetected chemical seeps? Each new dive, each camera deployed, each sediment sample collected adds a piece to a puzzle that remains almost entirely blank. The question also remains open as to what extent human activity is beginning to alter this supposedly pristine environment. Recent studies have detected microplastics and other pollutants in deep-sea organisms, including amphipods captured in trenches. Although the reference paper focuses on marine life and exploration, other research has shown that even in the most remote parts of the ocean, the products of modern industry and consumption are slowly seeping into the depths. The abyss, far from being a refuge untouched by our presence, is beginning to reveal the traces of the surface. At the same time, the prospect of economically exploiting the ocean floor raises questions about the impact such activities could have on ecosystems that are still poorly understood. Any disturbance of the sediment, any modification of deep-sea currents, or of the chemical sources that sustain chemosynthesis could trigger unpredictable effects on a very delicate ecological network. In an environment where processes are slow and regeneration can take centuries, the damage would in practice be irreversible on a human timescale.